Thank you for the introduction. Good afternoon, everybody. I would like to thank the organizers for the very nice meeting, and I would like to thanks for the opportunity to discuss and show you my work, our work. The title of this talk is Quantum phase and entangled generation in optical cavities. We are doing this work with collaboration of my colleagues Daniel Rossato, Fabrício Luiz, and Celso Vilas Boas. We would like to thank the funding agents, FAPESP, CNPq, INCT, Quantum Information, and UFSCar. So this talk was organized following this order. I will start to talking about the physical system and the model. I will give you some introduction and motivation, and explain more about the atom cavity system. And then my talk is divided. I will show you two different results, but it's connected. I will start to show you a controlled phase gate based on cavity IT, talked a little by Celso Vilas Boas on Monday. And I will show you, the implementation of the controlled phase gate, considering different setups. First, I will show you the controlled phase gate, considering classical and probe control fields, and then I will show you the phase gate, considering for single photons. And then I will show you how we propose an entanglement generation, considering two different setups. And then I will show you how we can do this theoretically. And then finally, I will show you my conclusions. The motivation of this work, everybody knows that in the classical computation, the bit can be assumed just only two values, 0 or 1. And differently of the classical computation, quantum computation, the quantum bits or qubits can exist in a state of a superposition. It means that can stay in two states at the same time. So, because of these properties, tasks performed by quantum computer can overcome significantly classical computation. So, quantum computing presents faster capability, greater storage capability, and composite quantum system can be present quantum correlation like entanglement. That will be very useful for quantum cryptography, teleportation, superdense encoding. So this allows the quantum computing system can be exponentially more powerful than classical computation. And because of this, a lot of countries and a lot of big, very important companies have been work with quantum computation, like IBM and Google. The physical system that we used to study here is an optical cavity composed by two mirrors, okay? And here schematic is an illustration of this cavity, optical cavity, where we have two mirrors, okay? That we can consider different configurations. It means we can consider, for example, the transmission coefficient can be differently. And here we present a emitter model like a 2-level system inside the optical cavities. Here gamma represent the dissipative decay of the quantum emitter, and G represent the coupling between the mode cavity and the emitter. Can be a single atom or a single quantum dot and other things. And kappa represent the decay of the cavity field. So this is among several systems that can be used to perform and can be used to do quantum device. This system represents a fundamental building block for quantum computation, because it's possible to do initialization and detection of qubits, that we can see some nonlinear optical phenomenon, and then we have a lot of applications. Like we can observe the cavity IT, we can perform quantum memory, quantum gates, and quantum networks. The physical system that I studied here, like I told you before, is a optical cavity assisted by external fields, okay? So we consider here, for example, a single atom inside, that in this case is represented by this diagram level, composed by three-level system. It's a three-level systems, okay? So here is represented the pumping field impinged on the cavity, and here is the atom system. So this represents a three-level system, the lambda configuration, where we have two ground states represented here by the state 1 and state 2, and the state 3 corresponds to the excited state. The state 1 and state 3 are coupled by G parameter G, and gamma 3.1 and gamma 3.2 represent the decay of the excited state. So here we are interested in a specific setup called single-sided cavity. In our model, this single-sided cavity can be modeled considering kappa B much smaller than kappa A. This means that this mirror is perfectly reflective, and the other one have a non-null transmission coefficient. The atom cavity Hamiltonian that represents this coupling is given by this expression. This is very, very, very familiar for everybody. And here, this terms is associated the free part, okay? This represents the coupling between the atomic system and the mode cavity, and this one represents the strength of the pumping field. Okay. And what we are very interested to show you here, we're using this system for implement quantum gates and a device that can generate entangled states. So a very important effect that we study in the system is the electromagnetically induced transparency. Okay. So here we put again the schematic representation of the atomic cavity system. And here we plot the transmission of the system. If, for example, if the light field is detected for the other side, and we put here the transmission function of the detuning. So when the G is equal 0, that corresponds, for example, to the empty cavity, everybody knows that when the delta P is 0, it means that the pumping field is resonant with the cavity mode. We observe the maximal transition exactly when delta P is equal 0. But otherwise, when we consider, for example, a single atom inside or a lot of system, we can observe, for example, when we consider G different from 0, we observe a normal mode splittings predicted by the Jaynes-Cumming model. Okay, so using this kind of system, a group from Germany, the Max Planck, demonstrate experimentally a protocol where we can induce a phase shift on a single photon, considering a single atom inside. Okay, in this case, they show experimentally a quantum phase gate between an atomic state represented by the 0 with superscript A, between the apolarization photon states represented here by this 0 with superscript P. So they show that it's depending of the atomic state and depending of the polarization of the photon state, is possible to induce a shift phase by pi. Considering this system, they show you that it's possible using the phase gate. It's possible to show the entanglement between the atom and photon. In our proposal consists that we can use a very similar way to induce a phase shift, but in our case we consider a nonlinear optical phenomenon explained by Celso some days before. So here I will briefly explain you what consists this effect. So electromagnetically induced transparency, called EIT, is an optical phenomenon which allows a drastic modification of the optical properties in atomic system by applying a control field. So it means that when we have another field applying of the system, that one that I showed you before, coupling, for example, this transition, we can induce a transparency regime. So it means that a opaque medium can be transparent when we inside a probe field, if the control field is there, coupled with the transition. And this we can show you in this dashed curve, okay? So when the atom is inside the cavity and the control field is on, we observe that the transmission goes to 1. So we observe a transparency window when the control field is on, and the IT regime is associated this. We need to consider this condition. Another system can be modeled using the same, like very similar configuration, and can be present very similar effect like I showed before. For example, a double quantum dot, vertically stacked. When here we observe is a experimental sample where the double quantum dot is in this case have a symmetric structural geometry where one is more narrow and the other is more wide. And we observe that controlling of the electrical field can the resonance, the conduction levels or the valence levels can be resonant, okay? So in this case, for example, the tunneling is favored. Otherwise, in this case, the hole can be tunneling between the dots. So for example, if we consider a properly structure where the tunneling is more easy, we can model, again, the three-level system, very similar that I show you. But in this case, the coupling between the state 3 and state 2 is associated with the tunneling between the dots. And we have a lot of, it's very similar effect, but when we consider some conditions, the optical properties change a lot, like showed for Celso Vilas Boas. So the first part of this talk, I will show you I propose that we can use the cavity IT phenomenon, the cavity IT phenomenon in order to perform a quantum phase gate. So the idea here is the following. So we have, again, the three-level system, and in this case, we consider the state 2 state 3 coupled by the control field, okay? And this field can be induced a phase shift of the input field. So we consider the optical cavity assisted by external field, that A in is associated the input field, and A out is associated the output field. So we have two possibilities here. If we consider the strong coupling regime, it means G is much larger than kappa, the decay of the rate, and the gamma. So in this case, we consider a single-sided setup for the cavity, and then the input and output field enter and exit from the cavity for the same side. So if the control field is off, we know that because of the normal mode splitting, we have the input field is reflected, directed, okay? But in otherwise, if we consider the control field, we can transfer the population from the system can be transparent for the system, and then the input field can enter in the cavity and then is reflected, okay? But in this case, in this first case, the phase shift, we observe a phase shift here by pi, while in this case the pulse field leave the cavity without changing its phase, okay? So we consider this configuration. In order to do our calculation, use the master equation. The Hamiltonian that describes this system, this coupling is given by this one in the interaction picture. And we use here the input and output theory in order to obtain the dynamics of the output field, represented here by alpha out, okay? And the connection between these two formalisms is given by this expression. And then we are very interested here in to observe what's happened with the phase of the output field. Here we consider the control field and the probe field classical, and we observe the acquired probe phase in pi units in function of the detuning. So we observe here the red curve is when we have the control field, and the other case when the control field is off. So we observe when we plot the difference of the phase when the control field is on or off, we observe this graph. Exactly when delta is 0, we observe the phase shift by p in this case, but we can observe in the mode, exactly in the mode splitting, this parameter is the order of pi, but in this case, it's not interesting for implement the phase gate because the atomic system observe the probe field, okay? So the properties is not preserving anymore. So in order to perform this phase gate, we consider the resonant regime. The next step, we show you. I will show you the performance of the quantum controlled phase gate, but considering the probe field a single photon, represented by the Gaussian pulse, and this multiplicative factor ensures that the pulse is normalized. It's a single photon. So we consider this, and using the input and output formalism, we combine the Schrödinger equation with the input and output formalism, and we put phenomenological the losses here, and this equation provides us the dynamics of the alpha out that we very interested. Yeah, here we plot the input field in function of the time, and the output field considering different values for the omega c. So we can see very different things here. The input field is the black one, and when the control field is off, we observe that we consider here a strong coupling regime. G is fixed by 10 kappa, and we observe the output field is reflected, okay? So and the shape is the same, yes? But when we consider the control field, but a smaller value, we observe the part of the field is reflected and the other part is transmitted, okay? So we observe as mismatching between the input field and the output field in this case. By the other side, when we consider a strong coupling control field, we observe a transmitted pulse. So when we compare these things, we can see that can induce a shift phase in the probe field, just turn on or turn off the control field. And why these different things happens when we consider different values of the omega c is explained by this inset. Here we plot the probe field that is represented in the frequency domain, when is represented by the dashed black line, and we observe the following. Here we consider the G fixed, okay? But the EIT window is directly proportional this rate. It means that when we consider different values of the omega c, we have a narrower or wider EIT window, okay? So in this case, when the omega c is 2, most part of the probe field is outside the cavity field. So some part is reflected. But otherwise, when the omega c is 10, the EIT window is wider, and then the probe field fits very well inside, and then the probe field is transmitted. Okay. And for the last part of this, about the quantum gate implementation, we considering how we can induce a phase shift, the same system, but consider single photons. In this case, we have a target photon. Okay, so the step 1 is associated when we send a control pulse, and we consider the control field applying in the system. So we have two possibilities. The control field photon is stored, because in this case, if we consider, we turn off adiabatically omega C, it's possible to store we can transfer the population from the state 1 from the state 2. But how we know that the state 2 is decoupled by the mode cavity? In this situation, when this situation happens, is the same like the empty cavity. So in this case, the pulse can be entered and then is transmitted, okay? So we have two possibilities. The control photon is stored and the atom goes to the state 2, or the control field is not stored and the atom stays in the state 1. The dark state of the system is given by this state. It means that if we turn off the omega C adiabatically, the state of the system goes to the 1, 1. That's associate the state 1 and the cavity, 1 photon inside the cavity. For the state, the atom in the state 2 and 0 photon inside the cavity. After that, we consider that the target pulse, here represented by the blue one, and we can perform it depending on the atomic state. And we can show the strong coupling regime. We can induce a shift phase by pi. And here I show you because in this setup we consider a combination of the memory process and the phase gate. Okay, so here we plot the control field in function of the time and the target and control pulse. And here we plot the population of the atomic state in function of the cooperativity that is directly proportional to the G square. So we can show you that we can perform it with very efficient quantum memory here when we consider the cooperativity very low, very high, sorry. And this control field was derived using the impedance matching when we consider the alpha out is equal 0, and then we can optimize and find a omega C that we can observe this performance. Here we plot the input and output field considering different state of the atomic state in function of the time, considering a very high cooperativity, and we observe the phase gate is implemented. Here we plot in function of the time, but considering different cooperativity, and we observe that exactly when the cooperativity is equal 0.5, we observe the alpha out is equal 0. So this corresponds to a lower bound of our quantum gate phase. Here we plot the number of the mean number of the atoms of the photons outside, sorry, and the scattering light, okay? And we observe here a dark region that this corresponds, for example, in this case, just 8% the light is detected outside, okay? So this is like a lower bound in this case. So the successful of the probability to perform our gate is given by this one. So we observe a close to 1 when the cooperativity is high. The last part of my talk, I will talk about the generation of the entanglement using the same setup. But in this case, we use the concurrency in order to quantify the entanglement. And everybody knows that when the concurrency is 0, the state is separable, while when the concurrency is 1, the states are maximally entangled. So the idea is the following. We consider now two atoms inside, described by the three-level system. But in this case, we didn't consider the control field. And we consider a different initial state. In this case, we consider that the initial state of the atomic system is a superposition of these two ground states. So the idea here is inside an input field, this is interacted, respected, and via control phase gate that I will show you, depending on the atomic state, we can show you that we detect the alpha out. And in this case, when the alpha out is detected, depending on the regime that we are in the system, we observe that the system can be maximally entangled. So the Hamiltonian that represents this coupling is given by this one, where A and B is associated to each atom, and the initial state for the atomic state is given by this one, and the cavity is considered empty. So induced phase, using the same idea that I showed you before, depending on the atomic state, the input field can be transmitted or reflected. So in this case, can be only when the atomic state is in the state 2, is imprinted a phase by pi. But in the other, sorry, I'm wrong. Just when the atomic state is the state 2, in this case is not coupling, so the input field is transmitted, okay? So without phase is induced. But otherwise, if the atomic state is another combination, the input field will be reflected, and then the difference between it will induce a shift phase of pi. So we can consider different things, this state, and then in this case, depending if we consider a strong coupling regime, the control field is reflected, but otherwise, the same thing happens if we consider this system, this state, and these things happens when we consider the atom state 2 or state 1, and if the two states, the atomic state are both in the state 2, we observe the control field is transmitted, and then for a strong coupling regime, the control phase flip is successfully performed. So when we consider the stationary regime, we have this state that is maximally entangled when we consider the coupling. So the atomic state is maximally entangled. Here we plot the concurrency for different values of the cooperativity in function of the time. And we observe that as the cooperativity is increased, we observe a maximum of the entanglement. And the black curve is associated of the input field. So the time to generate the entanglement depends on the pulse duration, okay? Here we plot the concurrence in function of the pulse duration, and we observe that we have a lower bound for pulse duration in this case. And here, this happens because here we plot the alpha in and alpha out in function of the time, and we observe for when we have a short pulse, part is reflected and part is transmitted. So we have here a mismatching between the shape of the pulse. Otherwise, when we have a long pulse, we observe this fact, and then the phase shift is performed. Here we plot the number of photons outside in function of the cooperativity, considering different states for the atoms, and we observe this curve. This happens because part of the light for the very low cooperative values is scattered. And then we observe the cooperativity is 1 when very close to 1 when we have cooperativity large. And the other setup, the last one, and now we consider the two single atoms in distant cavities, and we consider this setup. A single atom is is impinged in a beam splitter 50-50, and then the photon can go for the system or for this one. They interacted and respected that I showed you before, depending of the coupling regime, the photon can be transmitted or reflected. And then we consider this initial state, so the photon goes there or goes there. And the second step represents the interaction, where if the photon goes there, they can induce in the system. Otherwise, if these things happen, we can induce a phase shift in the other one. And we consider that the photon pass again through the beam splitter, and then we observe, depending where is detected the photon, the atomic state for the strong coupling regime, the atom is always maximally entangled. So it doesn't matter where it's detected. But it haven't not all been good. And we plot here the detection probability for both detectors. And then we can see for the state where, depending of the cooperativity regime, is maximally entangled always, but the detection probability is much smaller. So atoms are maximally entangled in the strong regime. Doesn't matter where it's detected. My conclusion, we have showed the theoretical implementation of the quantum gate. So consider the single-sided cavity. We showed a phase induced with single photons. And our results show that depending of the atomic state can be used to entangle two atomic states in different setups. And thank you for your attention.